Hi there. This video is about the fundamental theorem of calculus, the first part. So there are two parts to the fundamental theorem, and this video here is just going to talk about part one. And so the number one thing to talk about, first thing, is we're going to talk about this thing that's called the area function, or you can think of it as an accumulation function. So if you think about this definite integral here, we're trying to find some area. We're going from 1 to x. So you can see the upper value of the integral is not known. So we say wherever we stop, that's how we talk about this function. So this capital A means an area function. So I'm going to use this as our first example, just to get an understanding of what this means. So we can focus on the right-hand side and think about graphing this. I think that's a good thing to do. So I'm going to label this the t-axis, and we'll call this the y-axis. So you can see the function here that we're looking at finding the area under the t function. So y equals t. So sketch it right here. So it's very similar to just y equals x. So that's what it looks like. And so the area function begins at 1. So we're going to start calculating the area right here at 1. And then it's going to stop at an arbitrary value at t equals x. So we're going to put it right here. So it's this thing here. Right, I'll shade that in so you can see it. So that thing is what this function is. So this is a of x. And so I think if you think of it this way, you can see that you're integrating from 1 to an arbitrary spot, a of x. But this is an actual function where you can insert different values in place of x, and then you can calculate this, because as x moves to the right or to the left, the area is going to change. So let's do just a quick calculation. Because this is a function, we could do something like calculate a evaluated at 5. Right? We could just figure that out. So all that would mean is replace the x with 5. So I'm going to go right here and cross that off. So if we're now going from 1 to 5, then you can definitely calculate the area of this shape. So what I'll do for convenience is to break the shape into parts. So I'll draw a little line here. This is going to be 1. And then because this is the line y equals t, I'm going to come over here to the y-axis, and this here is going to be 5. So we have a rectangle down here. The width is 5 minus 1, which is 4, and the height is 1. So it's a 4 by 1 rectangle. And so that area is 4. And then the triangle on top, we have a base of 4, and then also the height is 4. So you can see it here, 5 minus 1. So here we could do 1/2 base times height. So 16 over 2, and we get an area there of 8. So we're done. If you want to calculate the area of this trapezoid from 1 to 5, you have to take 4 plus 8, so you get 12. And so that's the value of the area function at 5, right? If you use 5 as your x value. So this here is equal to 12. So like any other mathematical function, you could put different values in for x, and you would get different values from this picture and from the calculation. Alright, so what we're going to do now is to make this a little bit more general, and we're going to take this right into what we call the first fundamental theorem of calculus. So now, instead of talking about starting at 1, we're going to start at an arbitrary location. We can call it a. And instead of using a specific function like y equals t, we're going to use an arbitrary function. We'll just call it f of t. But the notation is the same. We're still going to call this the accumulation function or the area function, right? The upper limit of the integral is still x, so this is a function that depends on x. So I'm going to put a diagram up here, and we're going to use this to basically prove or establish what we call the first fundamental theorem of calculus. So here we have a diagram. We have this curve here. We're calling it little f. And you could integrate from a to b, for example, but we're going to go from a to x. So you can see a to x right in this spot. And really, to develop the first fundamental theorem of calculus, we're just going to find the area of this pink little strip. And so this pink portion looks like a rectangle, but it is not flat on top because it follows the function here, which is irregular. But we're going to take care of that by introducing, or by using the idea of a limit. So here goes. We're going to talk about this. So if you want to get the area of the pink little strip, we can use this area function not once, but twice. So you can see if you go from a to x, you'll get this green portion, which we're calling a of x. So what we're going to do is we're going to overshoot here. We're going to go from a to z, and then calculate the green and the pink portion, and then we're going to subtract out the green portion away. So if you want the area of just the pink strip, it's going to be a of z minus a of x. So you have to think about that a little bit, right? So a of z will have both the green and the pink, and then we're going to subtract this away. So it's going to remove the green part, and you're left with that skinny pink strip. And then what we're going to do here is we're going to play around a little bit. We're going to take a of z minus a of x, and we're going to divide by an expression. We're going to divide by z minus x. So if we look at this carefully, the areas that we see here, right? A of z minus a of x, these represent areas, and then z minus x represents the width of this little pink sketched portion there. So if you take an area and you divide by the width, then what you're left with in some sense is a height. And that's exactly what this represents. So this thing here is a height of some sort. And so the average height here is represented by the f function, right? So if you go from the x-axis to the function here, you'll be using little f. So you could call this f of z or f of x, right? But you'd have to estimate. So I'm going to write it this way. So a of z minus a of x. And then we're going to divide by z minus x. So area divided by width gives us a height. And I'll just call this f of z. So even if this isn't perfect, we could call it an approximation here. Okay, so now what we're going to do with this is we're going to take a limit. We're going to let z get very, very close to x. So I'll write this down. Let z tend to x. And what that will do with the pink strip is it will make it infinitely thin, right? Very, very small. And notice if z is going to go to x, then you can plug x in place of z on the right-hand side here, and it's just going to give you the function value, right, evaluated at x. Okay, so I'm going to move these things down here, and we'll finish the work to this. Right, so I'll write this out in front. So this is the limit as z approaches x of this expression. So it's a of z minus a of x. It's over z minus x. And so then we're going to take the limit here. So this is going to equal f of x. So this is the big stuff here. So you might remember this from a couple of lessons ago. Right, this is a change in y over a change in x, and z is tending to x, and this gives you that popular indeterminate form. So what we have here on the left-hand side is the definition of the derivative of this function, right, of the a function here, and the derivative is evaluated exactly at this location. So what we get here, just by definition, this is a prime of x, right, and that's equal to f of x. Get rid of this. And so I'm going to write this another way because this is often expressed in a different way. So if you have a prime here, you could say, using the operator notation, d dx of a of x is equal to f of x. And this here is actually known as the first fundamental theorem of calculus. So it's really telling you your rate of change of the area function, right? This is equal to f of x. So we can go back to what we had before. If you remember this result, right, this is how we defined the area function. So a of x is equal to this integral. So typically the way you will see this written in books is it won't be expressed this way, but instead of writing down a of x, we write down the integral notation right here. So really it's going to look like the derivative of this integral, right, is equal to f of x. So the common way you will see this, and so this is worth a look, because we have to look at it carefully. So it's saying the derivative of the area function, right, this is equal to f of x. And so this is the statement of the first fundamental theorem of calculus. So this I will call FTOC, part 1, right, the fundamental theorem of calculus, the first part. So the big thing, if you want to understand this in words, because this is a really profound statement, it's saying that the area function for f, right, that's this right here, the area function for f, this is an antiderivative of f, right? And you can see it probably best, that interpretation would be the statement in red. So you can see that the area function is an antiderivative for this function here. So just the area function for the function f is an antiderivative of f. And what it really tells you, if you look at this bottom statement, is that the concept of area and the concept of the derivative are actually inverses, right? One of them is going to undo the other.